Hello, my name is Asha Sheela, working as Assistant Professor in Chalpati Institute of Information and Technology. Today, I want to discuss the simple parallel algorithms. So, before going to that, see, I will show you the diagram here. So, here we have the number of processors are there. So here in this diagram we took the 27 as the number, and this is divided into two parts, 4 and 23, and after that the 4 is divided into again 2. And here means in this diagram, so here particular number is divided into n numbers in parallelly. So here 4. 4 is divided into 8 and minus 4, and also 8 is divided into 5, 3. Minus 4 is again it is divided into minus 6 and 2. In that way the entire numbers are divided into n numbers in parallelly. See here. So what is a simple parallel algorithm? Let us take an example here. We took an 8 numbers there and we start with 4 processors. Each of them adds 2 items in the first step. See, I will show in the figure here. And here each of them add 2 items in the first step. And after that the number of items is halved at every subsequent step. Hence, here we have the log n steps are required for adding n numbers. The processor requirement is order of n. How do we analyze a parallel algorithm? See here, the parallel algorithm is analyzed mainly in terms of its time, processor and work complexities. So here the time complexity, here we are showing as T of n, how many time steps are needed. And processor, for the process complexity, here P of n, how many processors are used. For the work complexity, we are taking W of n, what is the total work done by all processors. So for that we are taking an example here. Let us see. T of n, it will take, the time complexity is order of n log n. For the processor complexity, it is taking order of n. And for work complexity, it is taking order of n log n. So here, these are the time complexity, processor complexity and the work complexities in the parallel algorithm. And now how we can judge the efficiency, we will see here. Let us say here, we are saying A1 is more efficient, means A1 is one type of processor. It is more efficient than A2 if work complexity W1 of n is equal to order of W2 of n, regardless of their time complexities. For example, here let us see W1 of n is equal to order of n and W2 of n is equal to order of n log n. Here we are taking W of n is equal to order of n. W2 of n is equal to order of n log n. Now consider the parallel algorithm here. A1 and A2 for the same problem. For the A1, W of n work in T1 of n time. And A2 work complexity is W2 of n work in T2 of n time. If W1 of n and W2 of n are asymptotically the same, then A1 is more efficient than A2 if T of n is equal to order of T2 of n. See here, for example, W of n is equal to W2 of n is equal to order of n, means here we are taking the work complexity, but for time complexity here T of n is equal to order of log n, T2 of n is equal to order of log square n. Here the work complexity, time complexity is different, but here the work complexity is same. So that's why A1 is more efficient than A2. Now, if again we will judge the efficiency if it is difficult to give a more formal definition for efficiency. Suppose let us take the same situation, A1 and A2 are the two processors, and here W of n is equal to order of n log n, and the time complexity for the A1 T1 of n is equal to order of n, and for A2 W2 of n is equal to order of n log square n, and T2 of n is equal to order of log n. It is here from this it is difficult to say which one is a better algorithm. Though A1 is more efficient in terms of work, A2 runs much faster. In terms of work, A1 is more efficient but A2 runs much faster. So both algorithms are interesting and one may be better than the other depending on a specific parallel missions. Now we will see the optimal parallel algorithms. Consider a problem and let time complexity T of n be the worst case time upper bound on a serial algorithm for an input of length n. Assume that T of n is the lower bound for solving the problem. Hence, we cannot have a better upper bound. Consider a parallel algorithm for the same problem that does W of n work in T of n time. The parallel algorithm is work optional. If W of n is equal to order of T of n, it is a work time optimal. If T of n cannot be improved. Again, we will see the same diagram here, a simple parallel algorithm. Here we are adding n numbers in parallel. See, we saw the diagram here. The same number is divided into two two parts. And each and every number is divided into two parts, subparts, in parallelly. So from this, we will see a work optimal algorithm for adding n numbers. For the step 1, use only n by log n process and assign log n numbers to each processor. Each processor adds log n numbers sequentially in order of log n time. In the step 2, we have only n by log n numbers left. We now execute our original algorithm on these n by log n numbers. From this now, time complexity of n is equal to order of log n. Work complexity W of n is equal to order of n by log n into log n. That is nothing but an order of n. From this, in the next slide, why is parallel computing important? From this, we can justify the importance of parallel computing from the two reasons. Very large application domains and physical limitations of VLSI circuits. And also, though computers are getting faster and faster, user demands for solving very large problems is growing at a still faster rate. And some examples include here weather forecasting, simulation of protein folding, computational physics, etc. These are the examples of the parallel computing. And now we will see the advantages of the parallel computing. Here it offers the possibility of overcoming such physical limits by solving problems in parallel. In principle, thousands, even millions of processes can be used to solve a problem in parallel, and today's fastest parallel computers have already reached teraflop speeds. So from this, you can understand the simple parallel algorithm. So, thank you.